Hey everyone, welcome to Power. So we're continuing our study of work, energy, and power. And so first off, let's start off with a pretty basic definition of power. So all power is a rate of energy transfer. It's the rate at which work is done, and we call that power. Anytime we have a rate, as we talk about equations and whatnot, rate, there's usually some kind of time involved. And what we're talking about here is that power is transferred by any means necessary, and we'll talk a lot about that later. But the main equation is this. It's power is going to be the amount of work done in a certain amount of time. So for variables, we'll use it like this. P equals W for work over time. And this is kind of tricky, kind of confusing, because the units here for this is a watt or a capital W, okay? So the unit of power is a watt. It is a joule per second. That's what a watt is, okay? So we have a couple of pretty straightforward examples here. Our problem set's pretty good, so we're gonna leave you most of the time to work on that. But here we have an object that needs to be raised a certain distance at a constant speed, so we know there's no acceleration going on. And as close to 5 seconds as possible. So we have 3 power ratings, and all a power rating is, especially for electric motors, is it's just the amount of work it's capable of doing per second, okay? So what we're talking about here is power is work divided by time. And in this case, since it's an object being raised of a certain mass, it's going to be the force times distance divided by time. And because it is a constant speed, we've talked a lot about this, like we've had the cheerleader question and all that. The applied force is going to be the gravitational force. So it's going to be the force of gravity times distance over time, which is just mgd over t is equal to the power here, okay? So all of this, it boils down to power equals mgd over t. And then we start taking apart the problem. We're gonna look at the 1 kilowatt motor, and that's just 1,000 watts. And so when I take a look at this, what I have is the mass of the object, 193 kilograms. Gravity, 9.8 meters per second squared. The distance, d, so we're gonna have 7.5. And what we're gonna do here is we actually don't know what the t value is, right? We know it has to be done in 5 seconds or close to it as possible. And each one of these motors will do it at a different rate, hence their different power rating. So the first motor, this is the 1 kilowatt motor. So this is how we'd set that up. We would solve for t. And when you do the math, you get t is equal to about 14.185 seconds, so about 14 seconds. The 3.5 kilowatt motor is the same thing. We use the same setup, 193, 9.8, 7.5. The time is unknown, and I'm using 3.5 kilowatts or 3,500 watts. And when I crunch the numbers, I get a T of about 4.053 seconds, or about 4. Scoot off to the side here. And then for the 5.5 kilowatt motor, it's 193, 9.8, 7.5 over the time, and we set that equal to 5.5 kilowatts. Sorry, I ran out of room. And then I get a time value of about 2.6 seconds. And so to answer the question, which motor is best, so which one did it as close to 5 seconds as possible, the first motor, this was too slow. The last motor, the 5.5 kilowatt motor, this did it too fast. And it looks like the 3.5 kilowatt motor was just right. So the 3.5 kilowatt motor is best for this particular job here. All right, so there's one kind of example. So just know that typically something is being lifted up. That's the problem we're gonna see a lot of times. It can also be pushed to the side and all that. So just know that's what we're gonna get for those, okay? There's an alternate form for power. So remember, power is work divided by time, work per time. And we know this is a watt or a joule per second. Well, work can also be expressed as a force times distance, still over time. And if you notice, we have this quantity here, distance divided by time. Well, distance divided by time, that's velocity. So the other form of power that we can use is force times the velocity of the object. This is still in watts. We would still measure this as a joule per second. Some of the variables, though, just might be easier to say force and velocity, since we're pretty good at finding those now. So here's an example. We know we're going to use this power is equal to force times velocity. So take a look at this problem. We have a person doing a pull-up. We have the distance and we have the time. So for the force, we know the force is going to be Fg, which is mg. So I got that guy there. So Fg, mg is 42 times 9.8. So it looks like we get about 411.6 newtons for the force of gravity. And since I know velocity is distance divided by time, I'm given a distance value of 0.25 meters and a time of 2 seconds. So I get a velocity of 0.125 meters per second. So plugging that into my alternate form of power equals force times velocity. The force is 411.6. The velocity was 0.125 meters per second. So I get a power of about 51.45 watts or joules per second, right? So when we tackle our lab next week, we'll have a better understanding of how that works. All right, if you have any questions, let me know. Thanks for watching. Bye.